And hello. So again, my name is Joey, and I'm going to be your trigonometry and calculus or pre-calculus, sorry, teacher for one class for the session today at 10 a.m. Yes, today we are doing another session on pre-calculus. So this is the U.S. curriculum, and this is our second session together. So I believe I did one on Thursday, and we're just going to continue with that material. So if you're tuning in for the first time, welcome to the stream. This is one class where we have free lessons for you at oneclass.com/livestream. We're live streaming about 7 days a week, and we're helping students all across the world to catch up on material or to get ahead in a material, depending on where you are at in the secondary school level. Currently, we're doing math and chemistry, and specifically today, again, my name is Joey, and I'm going to be doing with you pre-calculus for the U.S. curriculum today. So let's get started, and we'll continue off where we left off kind of on Thursday. So as a recap for last lesson, what we did was we talked about this concept of continuity and discontinuity. So just a little review about that. We have continuity is where we have x. We have kind of x. The variable x is defined for all x's are defined for a specific y function. So if we had an f of x, for example, like if you had a quadratic equation, a quadratic function like this. Sorry. Uh, like like this over, oh, sorry, let me get used to this. Oh, sorry, it's just a little finicky with the board here. Try this again. Oh, why does it default to this? Let me just refresh this, sorry. All right, there we go. So if we had a quadratic kind of function like this, where we have here, this is y equals x squared, for example, x squared. This function is continuous for all x regions, because if you subbed in a particular x value, you would get a defined y value in this case. Sorry, this is supposed to be equal sign, not a colon. And then we talked about this concept of discontinuity. So remember, we had three types of discontinuities. We had removable, we had infinite, and we had jump discontinuities. And we briefly talked about what it means to be, what it means for a function to be discontinuous. So if x is not particularly defined at that specific region, at that specific point of x, or if it was defined but it was not expected value, such as in a jump discontinuity. We also talked about this concept of infinite discontinuity and how vertical asymptotes provided a good kind of clear definition of what an infinite discontinuity was. So that's just a little review of what we did kind of last session. Today we're going to jump into this concept of extrema, so an increasing and decreasing functions. So I'm just going to erase this, and I'll define some terms before we start today. But this concept of extrema. So when we talk about extrema, we're talking about this concept of minimums and maximums, and we're already familiar with this term, minimums and maximums. So I'm going to define it as points on the graph that are, we can say minimums or and maximums, actually not or, and minimums. So give me a second, you can't see that, but here you go. Points of the graph which are minimums and maximums. So when we're talking about extremas, there's kind of two types of extrema. There's a local, and then there's a absolute. So let's define these two terms before we start. So a local maximum just means that it's kind of, you can think about it as it's both of them are extrema, sorry. So both of them have minimums and maximums. So when we talk about a local max or a local min, we're talking about a function that approaches a point which is its highest point in that particular function. However, this isn't the absolute minimum or maximum, because it's not the highest, like when you think about it as a y value of that point. It's much easier to see this with an example when we look at a graph. So I'm going to use this question one as an example. But when we talk about approximate the relative extrema of each function, a local maximum, for example, or a relative maximum. You can use another word such as relative. In Canada we use local, but you can use relative as well. So I'm going to take this as a erase this and put relative here. Or a relative maximum. You can think of it as this function here in question 1. A relative maximum, for example, would be this point here at, this would be negative 3 and negative 1. Just because you had this function approaches this, you can think of it as a maximum point of this function, but it's not necessarily its absolute maximum, because as we know, this kind of arrow here goes towards positive infinity. So technically the absolute maximum, if you think about it, it's not a defined point, but it's positive infinity. But the local maximum in this case would be negative 1, negative 3, just because the function approaches a point that has a like greater y value before it goes into like a increasing before a decreasing y. So I'm going to write this definition as it's a point, so point where basically the function starts decreasing. So I'm going to make a little more room, and I'll define increasing and decreasing as well, because if you're not familiar with those terms, then it might be harder to understand this concept. So point where it switches, so it's increasing, point where it goes from increasing to decreasing. And this would be specifically for local maximums, but then if you have a local minimum, it swaps. So, or you can think of it as, or for a minimum, this would be from decreasing to increasing. So for example, if you had a local minimum if I take number 1 as my example here, my local minimum in this case, so my function is going to travels towards negative infinity. You see my cursor, so it's good. It travels towards negative infinity in this y value here, but it goes up. It touches here this point negative 1, so that's going to be my relative or a local maximum in this case, and then it's going to start traveling down. So this function was increasing before, and now it's going to decrease down. So it's traveling all the way up, and then it's going to decrease down. And when it decreases down, it hits just this point at x equals 1. X equals, I believe, 1 here, negative 4. It looks like a little parabola shape that we got, a little curve here that we get. So this point is going to be our local minimum. And now how do we know it's our local minimum? It's going from this, it meets this requirement where it says it's going from decreasing to increasing. So from decreasing to increasing. So you can see here, my y values are decreasing. In this case, it's going from negative 2 to negative 3 to negative 4 here. And then it's going back up. It's going back to negative 3 and then negative 2 here. And then it's going back towards 0 and then towards positive infinity. So it's going from a period of decreasing to a period of increasing in this case. So you're going to have, that's going to be our local minimum in this case. So what we have here is for question 1, I'm going to write this down here. So this would be, here, let me scroll down for a bit first. So this was question 1. So for question 1 here, we have a local or relative maximum. So our relative max, we defined it as, our relative maximum was this point here, this little, because it was going from increasing to decreasing, because I'm going from increasing, I'm going from negative 8 to negative 6 to negative 4 to negative 2, and then it's going back down. So this would be our relative maximum, and this here we define this point as, this was negative 1, no, sorry, this was negative 3 and negative 1, I believe. It's a bit hard to see, but it's negative 3 and negative 1 in this case, and then our relative minimum in this case was, we defined it as this point here, right? Because it was a period of decreasing and then it's going towards a period of increasing. And this point here was, this is 1, negative 4 here at this little point here. So it's 1, negative 4. And that's going to be our answer for question 1. So before we get into question 2 and these other questions, we're going to define a couple more things here. So I'm going to define what an absolute maximum or minimum is. So this is for absolute. I'm sorry, this is cut off for you, so I'll move this here. But for an absolute kind of minimum maximum, this is the function where it's absolute, or the maximum in this case is its greatest point. So for it's not a point where it's like positive or negative infinity. So it's a bit, sometimes a local max could be an absolute max as well, or a local minimum could be an absolute minimum. That's not always the case. We're defining absolute as the function's highest point or the lowest point. That's not positive or negative infinity. So this is function's highest and lowest point would be its absolute function, absolute maximum or minimum. So again, maximum for highest, and then minimum would be for the lowest. And some of the times you're not going to have an absolute maximum or minimum, but it's good to also know, because these will be our functions. They sometimes have you have local points and you have absolute points as well. And sometimes local maximums or relative maximums could be absolutes, but absolutes will usually never be local. Probably never be local, because it's going to be absolute for sure. And these are good. These are good things to know about a graph, because we know if a function is increasing or decreasing. And basically the concept of extrema, or minimums and maximums, is a switch from increasing to decreasing. So I'm going to highlight this in blue, because this is an important point here. So when we go from a period of increasing to a point of decreasing, we have this would be, I'm going to do this in red. From increasing to decreasing would be a maximum. So just like we did in number 1 here, this would be a maximum. And then from decreasing to increasing, we have this period of that point at which it switches from decreasing to increasing would be its minimum here. And this is important for pre-calculus, because what we can do is right now we can just do it graphically, where we can kind of visualize, we kind of plot the graph, and then we think of it as, oh, okay, where's my maximum or where's my minimum? But with the tool of calculus, and when we start talking about derivatives, and we start talking about the properties of derivatives, it actually allows us to solve this algebraically, and we'll get to that in a later stream. But what we can do is that we can actually take the algebraic expression for this function here, and what we can do is, if we find the derivative of that function, we can actually determine its local mins and local maximums very, very easily. But for now, we're going to stick to doing it through the graph, just so you can get the hang of it before we jump into the algebra, just because, again, algebra is a bit more conceptual when we work with variables. However, in a graph, it's a bit more visual, so it's less abstract when we talk about these specific things. So let's do number 2. So we're going to move on, and we're going to start doing, some of these questions over here. But so let's do number 2 here. So number 2 here, we have this function. It's going, as I can see here, from our previous stream before, we had, I'm just going to zoom in for a bit for the people at home here. Sorry. Yeah, there we go. So we have question 2 here. We can see we have a vertical asymptote. So I'm going to start listing properties first before we kind of define what the relative max and relative min here is. We have a vertical asymptote. This is x equals -1, right? So we can write here, this is a VA at x equals -1. Or we can say, remember, if you tuned into my previous stream as well, we have a infinite discontinuity at x equals -1. So we have this vertical asymptote, or an infinite discontinuity at -1. And then what we have here is we have kind of a rational expression, right? We have kind of the two little L's here that define what a rational expression is, but we don't know the equation, right? So I'm just assuming that this is a rational expression. It could not be, but it kind of looks like it in my opinion. But what's important about this? Let's do the minimum and the maximums, right? So again, when we define minimums and maximums, these are periods where it's going from increasing to decreasing for a maximum, and then decreasing to increasing for a minimum. So let's do maximum first. So let's write down its relative maximum. Because in this case, we don't have an absolute one. We don't have an absolute maximum or minimum, because if you look here, it's heading towards positive infinity, and this down here, and when x approaches infinity, y is approaching negative infinity. And we'll talk about end behaviors probably next video, but that's just a little preview about how we know it does not have a absolute maximum or minimum, or if it does, it's a positive infinity. It's not a specific defined value in this case. So what we have here is we're going to do this is a relative maximum minimum. So I'm going to write here. So let's do the relative maximum first. Relative max. So in this case, our relative maximum, as you can see, this is a period of decreasing, because it's this is a period of increasing, and so we're going up. Or you have -8, -6, -4, -2. It's going all the way up. It touches the 0 point, and it's going into a period of decreasing, right? And that's actually going to match my definition here. Remember, it's increasing my y value here, and at this point at 0, 0, it's going to start decreasing my. It's going into a period of decreasing. So in this case, my relative maximum is 0, 0, right? It's increasing up till 0, 0, and then it's decreasing after 0, 0. So in this case, my relative maximum is 0, 0. And let's do a relative minimum, because we also have a relative minimum as well. And a lot of times what we do is some functions might have both relative maximum and minimums. Some of them might just have one max, might just have one min. Some of them might not have a relative maximum or minimum at all. So you really, really need to be careful when we analyze the graph. You need to make sure it matches the definition of what a maximum is, what a relative maximum is, and what a relative minimum is. So let's do minimum first. So again, this was our maximum here. And this other point is we're kind of curious about is this point. So let's see if it matches our definition. So as we're heading towards, this is the point here, this is -2, this is x equals -2, 2. It's going into a period of decreasing, and then it's going to a period of increasing after -2. So in this case, it does match my definition of minimum. Remember, it's going from decreasing to increasing. So in this case, so we have a period of decreasing. It's going from, I guess here it's 5, or I guess here it's positive infinity, and it's heading to down towards 4, and then all the way till 2, and then that approaches its lowest point, and then it's going to increase. It's 2, 4, 6, and then it's going to positive infinity. So in this case, we do have a relative minimum at this point here. So this point here is -2 and 2. So we know our relative minimum here as well as -2 and 2. So that's kind of just two kind of questions is when we talk about these functions here. I hope we're going to do a lot more practice problems with this concept, because I know it is somewhat abstract when we talk about, how do you define a period of increasing? How do you define a period of decreasing? How do you know if it's maximum or minimum? So we're going to do a little bit more practice on this topic before we jump into kind of the next topic here. Because a lot of this, again, a lot of pre-calculus is we're going to build upon these foundations. And as we look at more functions, we're going to talk about things such as like end behaviors, things such as domain, such as range. And we're going to throw in continuity. We're going to review continuity again, and then they can ask you, what about relative maximums and minimums? So we have to make sure that this concept is kind of solid before we start adding stuff. Because if this foundation isn't solid before, we're gonna start losing track of things. Because they can ask you many properties of specific functions, and we need to be able to define each of those properties. So let's do. I'm not going to do 3 and 4 just because it says use a graphing calculator, and we can all use a graphing calculator. If you had like a TI-84, for example, maybe at school, a TI-84 is this kind of the standard graphing calculator. What you can do is you can just plug in this function here, and then just visualize it on your calculator. What I usually do is the website that I usually use is Desmos, and Desmos actually is kind of a nice graphing calculator, and you could plug that in at home, and you can kind of do that as well. But let's do number 5, because number 5 already gives you kind of a function here. So let's do number 5. So number 5. So let's look at our graph here. We have kind of a this is heading towards, I believe, positive infinity, and this is heading towards negative infinity here. So let's look at the intervals. So it's to approximate the intervals where the function is increasing or decreasing. So before we talk about, this isn't technically relative max or relative min. This is the concept of increasing, decreasing. So increasing means that again, my function is increasing in terms of its y value, or if it's f of x value, it's increasing as x goes. Could be going towards negative infinity or going towards positive infinity. If the f of x or y value is increasing, then the function is increasing. If I'm going towards negative infinity or to positive infinity, my y values are decreasing, then the function is decreasing. And again, we use these terms increasing, decreasing when we talk about calculus, because when we're familiar with calculus in this case, we come back to these two concepts a lot: increasing, decreasing, relative max, relative min. But I could define you in terms of when we talk about calculus, when we talk about a derivative of a function. If I take the derivative of a function and I plug in a specific x value, and if it's a negative value, then I have a decreasing function. If I have a positive value, it's an increasing function. Don't worry about that terminology. We will get there when we talk about derivatives and what they mean. But that's kind of just a sneak peek as what we're doing and why we care about increasing and decreasing functions. So at number 5, we have again back to the question. We have here this kind of this curve, and as you can see, this is a period of increasing, right? As x heads towards negative infinity in this case, the arrow indicates that it's increasing. So that arrow is increasing. It's heading towards negative infinity, and as we go, it's going to land on this little curve here. This little curve here, and then this period here is increasing. So I'm going to approximate this point as I'm gonna actually do a step forward, and I'm gonna give you the relative maximums and minimums as well. So in this case, if it's a period of this would be from decreasing towards increasing, this would be a minimum, right? So this is a relative. Sorry, my V is really bad. Relative min. And this was this here. My point here is -4 and -2, right? -4 and -2. And what about relative maximums? Do we have a relative maximum in this case? Let's find out. So do we have a period where it goes from increasing to decreasing? And we do, right? So if you look here, it's increasing here, and then it's going to up to this point here. I believe it's 4 and 2, and then it's going to decrease back down. It's going to, my y values are going to decrease, right? It's heading towards, this arrow is heading down, so it's heading towards negative infinity. So in this case, I'm going to say that my relative max is, if I approximate this point here, again, it's approximate because I don't know if the graph's super accurate, but this would be 4 and 2 right here at this point. So I'll do 4 and 2 here. Sorry. 4 and 2. And what we can do is we can actually find out, we can approximate the intervals where each function is increasing, decreasing. So now if we know these two pieces of information, we can actually do these intervals. So let's do increasing first. So where my periods are increasing, and I'll do this in blue because it's a different concept. So I think I should have color coordinated maximums and minimums, but it's okay. So at a period of increasing, so let's see, where is my function increasing? So as I said before, this period here is increasing, and then this is decreasing. This one's decreasing as well. So we only care about this interval from -4, which was the relative minimum in this case, -4, all the way up to +4, because +4 here is switching from increasing to decreasing. So in this case, my interval is from -4 to 4. So when we talk, this is a new notation that's that might be familiar. Some of you might use square brackets to do that. Oh, it's only between these specific points. But again, this isn't how this is a different notation. So when we write here -4 to 4, it's saying these are both x values. So I'm just going to clarify that for those who are not, if you're not familiar with this type of notation. When we're writing specific points here, relative maximum and minimum, remember, traditionally this here is my x value, and this here is my y value. When we talk about increasing and decreasing, or intervals of intervals specifically of increasing, decreasing, we're always talking about the x value. So in this case, this is always the x value. So this is not x, and this is not x, and it's not a point on the graph. It's not x and y. It's a period or an interval where this is these are the x values. Sorry, that's plural. So from -4 to 4, the period is increasing. So I just want to clarify that before we moved on. So again, these are not specific points on the graph. They're simply intervals. So let's do decreasing now, because we did increasing. So for decreasing, if we said here that the function was increasing, our other points, our other intervals, must be decreasing, right? So if we have here, if we extended this graph here, this would be like maybe up here, and this would go down towards -4, right? So this is a decreasing function. In that case, we can denote that as x is negative infinity. So we can do it's negative infinity, and it's decreasing all the way to -4 in this case. So that's one of my intervals. So I'm going to write that down. From negative infinity to this point is -4 is my decreasing. This is my interval of decrease, but we also have another interval of decrease, right? Remember I said this was a decrease, increase, and then because we had a relative max in this case, it was a period of decreasing after, right? So we have to account for that interval as well. So from 4, this was my relative maximum, it switches, right? It switches from increasing here, from -4 to 4, and then it's going to decrease, right? Decrease from 4 all the way here, you can say positive infinity. So in this case, we have two intervals of decreasing. It's going from 4, but +4, to positive infinity. And that here is our intervals of increasing and decreasing, right? It's decreasing from negative infinity all the way to -4 here. It's going to increase from -4 to 4, and then it's going to decrease from 4 to positive infinity. And those are our intervals of increase and decreasing. And what we can do, and as you might already can connect, if you can connect dots, what we have here, it's going to be decreasing first. And again, it's decreasing from -4 to -4. We approach, or we get to a relative minimum of -4 and 2. It's going to then increase from -4 to 4. It's going to approach a relative maximum of 4 and 2, the point 4, 2, and then it's going to decrease again from 4 to positive infinity. And that's what we're doing. What we're doing here. So these relative minimums and maximums can help us with our intervals of increasing and decreasing. So let's do one more. Let's do number 6 here. So let's see, number 6. So number 6 here, if you look at this kind of function here, it looks like a kind of something you would get in like a polynomial function. A polynomial function would have kind of this shape here, like specifically it might be a quartic function, just because our x to the 4 might have some behavior like this. And we know that because we haven't talked about even and odd functions yet, or polynomial functions, and we'll get to that later on in this course. But this looks like a power function, or it looks like a polynomial function specifically, and it's going to be it looks like kind of an x to the 4, but you don't need to know that until later. So let's just do this first. Let's approximate the intervals where functions increasing and decreasing, and I'm going to throw in let's also kind of solidify our concept of relative maximum, relative min. So let's do relative maximum first before we solve that, because it's going to help us with our intervals of increasing and decreasing. So let's do max first. Relative max, so relative min, and then we're going to do increasing, or intervals of increase and then decrease. So these are the things we're solving for, right? So let's do this. So we have a local max. Do we have a relative max or an absolute max in this case? We don't have an absolute maximum, because this is heading towards positive infinity and this is heading towards negative infinity. So we don't actually have a relative max, but we actually do have an absolute min, right? Our absolute minimum in this case, so it's actually not a relative minimum in this case. So I'm going to erase that. It's actually an absolute minimum. And how do we know it's an absolute minimum? In this case here, we have, this point here and this point here at, this x value is -1 and this is +1 at 1 here, the y value is 1. This is the lowest this function will go. It will not head towards negative infinity in this case. There's no arrows denoting it's going towards negative infinity. My function here exists, again, it exists in this kind of little curve here, but it's not going to go below -1. So in this case, we actually have an absolute minimum. So I'm going to write absolute here. Absolute minimum instead of a relative max. And again, in this case, it's an absolute minimum. So it is a specific type of minimum, but it's an absolute minimum, not relative minimum. In this case, we have 2 points in which it's an absolute minimum, which is nice. So let's do relative maximum first. So relative maximum, again, if we follow the curve here, it's going from, again, increasing to a point, going from an interval of increasing to an interval of decreasing. So in this case, it's going from, I have here, if you look at this point 0, 0 in this case, it's going from increasing, it's a very, very small interval, but it's still an interval nonetheless. It's increasing from, I guess this is, this would be x equals -1 to 0, and then it's decreasing after. So in this case, our relative maximum in this case is 0, 0. And our absolute minimum, as I talked about before, my function here does not go past -1, my y equals -1 here, right? So it does not go past this this little line here. So in this case, my absolute minimum, I'm going to have 2, right? Because I have 1 here and 1 here. So I'll define that as, and we can check that first before we go that. This is an interval of decrease, and it's going towards an interval of increase as well. As small as it might be, it's still an interval. So we're going to say here absolute minimum is, this will be -1, -1. I forgot the comma, silly. So this is -1 and -1. And we have also another, actually I'll make this smaller so it fits on the screen, -1 and 1. And this point here is 1 and -1. So these are both my absolute, sorry, you can't see that. Both my absolute minimums. I have 2 absolute minimums in this case, which is nice. And then let's do my intervals of increasing and decreasing. I'll do this in blue because it's a different concept. But let's check. So my intervals of increasing, for example, I have here, and again, I can use my relative maximums to help me out, right? Maximum states I have an interval of increase and then an interval of decrease after. So at 0, 0, I have an interval of increase first and then decrease. And we only care about increasing for now. So let's do this interval here. So I want to define what this interval is going to be. X is going to be -1 towards 0, right? So this will be a increasing interval of increase. So from -1 to 0, remember these are both x values, right? And what other points? Are there other intervals of increase? There are, right? Because I have an absolute minimum here at 1 and -1. It's going from decreasing and then it's going from to increase, right? So from 1 to +infinity will be my other interval of increase as well. So let's do that. Let's write that down. So it's going to be -1 and 0. I'm going to write comma, and I'm going to write here 1 and +infinity as well. So it's going to be 2 intervals of increase. So I have 1 here. It's going from -1 to 0. So as increasing, this will be decreasing. We'll get there, and then we'll be back to increasing. So let's see. What about my decreasing interval? So again, I have. We're going to use the minimums as well. So we have -1 and 1 here. So again, we have an interval of decrease. We defined it as an interval of decrease first, and then an interval of increase. So let's do. So this interval here is a decrease, right? So I'm going from, this is -infinity as x approaches -infinity, and it's going all the way to -1. So this will be -infinity, and sorry, that's a comma, -1, and I'm going to write comma, and I'm going to say that it's decreasing, and then it's increasing, and then it goes back to decreasing before it goes back to increasing, right? So this interval of decrease here, and as I know here, I can have a relative maximum, right? Of increasing, and then it's decreasing. So I'm more focused on this interval here. It's going from 0 to 1, right? And that's going to be my interval of decrease as well, from 0 to 1. So I've solved for my, again, relative maximums. In this case, I have an absolute minimum, 2 absolute minimums, because they both reach this point of 1, when my y value equals 1 here. And I have an interval of increasing and then an interval of decreasing. This should say decreasing. Sorry, this is going to bother me, so I'm going to erase this and write decreasing for you. So this is decreasing here. So I've solved for all 4 of these ones, which is awesome. So I'm gonna skip again. I'm gonna skip the graphic calculator stuff, and I'm gonna do these functions here. And these functions are a bit harder, but they're not as hard as you might think they are. So I'm going to do a couple of these ones, and that's going to be the stream for today. So let's do number 9. We can go in order if we want, and let's see how much we get done for today in the next 20 minutes. So we have, and this graph actually gives us the algebraic equation as well. So we know that this is a rational expression, which is awesome, and we can kind of know that, right? We know that this is absolute, this is a rational expression, and specifically a reciprocal of a quadratic, right? We have kind of the 2 L's, and we have this parabola here, so we know it's a reciprocal of a quadratic function. If you don't know that, I believe we do go over reciprocal functions in either, you might have already done that in your previous math course, or you might have, or we'll do it in this course. So I'll have to look at the other units and find out for you. But what we're going to do is we're going to approximate the relative absolute extrema. That's what we've been doing before. And then afterwards, we're going to approximate intervals of increase and decrease. So literally what we were doing before. So let's look at this graph. This graph here, we have, let's do our relative maximums and relative minimums first. So in this case, it's relative and absolute extrema. Let me clarify this as well. It's relative absolute, and we might have an absolute or we might not have. So let's write relative for now, and then we'll erase it if it's not relative, or sorry, we'll erase it if it's absolute. So this is relative. So we have relative max and relative min, right? So let's figure it out. So let's look at any period. And do we have a point that has a relative maximum? Let's check. So remember, relative maximum is period of increasing and then period of decreasing right after. So if I'm gonna look at my graph here, I have a period of, this is decreasing, and it's always decreasing in this case. No, in this case, this is increasing here. It's increasing towards 0 here, and then it's decreasing, but I don't have a maximum here. There's no point where it's going from increasing, decreasing. This is always a period of increase, and this is always a period of decrease here. So I don't have a maximum or a local max here. And then if we look at the U here, this is going to be a minimum, right? This is an interval of decrease and then interval of increase. So again, in this case, I actually have no relative maximum. So if you have no relative maximums, I can have no absolute maximum as well. So I'm going to write not applicable in this case, or none. Let's write none. None. No, right, exclamation mark. None. And this is no relative max and no absolute maximum. Because if we don't have relative maximum, there's no way we can have the absolute maximum. Yeah, that makes sense. No relative max means that I definitely don't have a absolute maximum. But do we have a minimum? Let's check. We do, right? In this case, it's going to be an interval of decrease and an interval of increase right after. This point here defines what that is. And I'm going to solve for this point, actually, and we can do that, right? We can do this point here. I'm going to assume here this is x equals 0, but I don't know what my value is. It's awfully close to 1, but I don't think it's 1. So let's actually solve for our relative maximum in this case. So if I subbed in x equals 0 into this algebraic expression, and I can solve for this because I'm given my algebraic expression. So this is negative 3 over x squared minus 4. In this case, I'm going to sub in x equals 0 to find out my y value, right? So let's do that. And I'm going to make some more real estate here and shift this up. But let's solve. So we're going to plug in x equals 0, right? So in this case, y equals, this is negative 3 over, I'm going to plug in x equals 0. So 0 squared minus 4. 0 squared is simply just 0. 0 minus 4. And this will be negative 3 over negative 4. That cancels out, which is 3 over 4. So in this case, my relative minimum, I can say here my x value is 0. And then it's going to be 0.75 or 3/4 if you want. But in this case, I'm going to keep it in decimals because I think it's a bit nicer. But it doesn't really matter. In this case, 3/4, 0.75. I'll take either answer. So this is my relative minimum. In this case, this is 0 and 0. And My x value is 0, the point 0, and then 0.75 is my relative minimum. So let's do my intervals of increasing and decreasing. So this will be my increasing. Let's do increasing first. Increasing intervals. So let's do it. So again, this interval, it's going from 0 all the way to -8. So this is a decreasing interval. This is a decreasing interval as well, and then it's going to head towards increasing, right? So in this case, because it's heading towards positive infinity, so I do have a interval of increase. So it's going from my relative minimum here, which was 0.75. So it's going from 0 all the way to this vertical asymptote, right? I have an infinite discontinuity at 2 here. So in this case, so my increasing would be from 0 to 2, right? From 0 to 2, because this is going from 0 to positive infinity. It's an interval of increase. So from 0 to 2 is my first interval. And do I have a second interval? I do, right? I have this here is a period of increase, right? It's going from -infinity towards -8, -6, -4, -2. My numbers are getting bigger and bigger. So in this case, I have a period of increase, right? So this is from 2 to positive infinity, right? So these are my intervals of increase, right? This here is my increase periods of increasing. This here is also my increasing intervals. So that's awesome. So I have 2 intervals of increase. And then for decreasing intervals, I'm going to have, again, this here is a period of decrease, right? So this here this is -infinity. If x is -infinity, it's going to decrease all the way to -2, right? My x values, right? These are all, again, I'm only working with my x. I don't care about my y in this case. As long as my y numbers are decreasing, then I'm going to write the x values, right? It's the x values at which the y values are decreasing. So in this case, this is -infinity, and then it's going towards here. It's going towards -2, right? This is always decreasing here. So it's -infinity to -2. And then I have, again, this is also a period of decrease, right? Because again, my relative minimum here is 0.75. This will be a interval of decrease before an interval of increase, right? So this interval here would be from -2, to 0, right? This is -2. It's heading towards 0. Heading to 0, sorry, not heading towards. So this is -2 to 0. And those are going to be my intervals of increasing and decreasing and relative mins and max. In this case, I have no relative max. I only have a relative minimum. I have increasing and decreasing intervals for question 9 here. So let's do, maybe let's do 2 more if we can, before we conclude for today. Let's do number 10. Number 11 is pretty simple. If it's just a quadratic function, it's just only one relative max in this case. But let's do or in this case actually it's absolute max. But we'll focus on number 10 first, actually, because it's slightly harder than 11. Try to tackle the more difficult ones for you, or at least things I can write about or teach about in this case, just for you guys at home. So I have here again, we have a cubic function, right? We have x cubed minus 3x squared minus 3, right? So let's do our relative maximums and relative minimums first. So let's do relative. I'm still not used to writing on this. I bought this recently, and it's kind of like a pencil, but it's not really. But still getting the hang of this. So again, relative max. Do I have a relative maximum? Do I have a period of increase and decrease right after? I do, right? This is a period of increasing here, and then a period of decreasing right after. My y values are increasing from bringing infinity to negative. This is, -3, and then it is decreasing right after. I have a relative maximum here. This point is 0 and -3. So I have a relative maximum of 0 and -3. Do I have relative minimum? I do, right? I do have relative minimum. This is a period of decreasing and the period of increasing right after. In this case, this is 0.2, -7. So this is 2 and -7. And let's do my intervals of increasing and decreasing. So this is increasing and decreasing. Actually, I won't do decreasing for now, but let's do increasing. Just I don't want to run out of space here. And oh, sorry. So I'll shift this guy over here. Okay, so let's do my intervals of increasing. So in this case, if I had a relative maximum at 0, 3, this period has to be a period of increasing before a period of decreasing, right? So this is a period of increase here. It's going from negative infinity, because this is going towards negative infinity, but as I move from x toward negative infinity towards this here would be towards 0, right? So that's going to be my period of increasing from negative infinity to 0. It's going to always increase. It's going to always basically increase, because if you extend the graph here, it's going to be going up and up and up towards 0, right? So that's going to be my period of increasing. Do I have another period of increase? I do, right? This is increasing and then decreasing and then back to increasing, right? So in this case, I can use my relative minimum again. This is 2, -7. So in this case, this is 2. It's going towards infinity as well. So this is 2, infinity would be my another period of increase. So 2, this positive infinity would be my next interval of increase. And then decreasing is really easy, right? Because decreasing is the one interval between 0 and 2, right? Because this is my decreasing interval. It's increasing all the way up to 0. It's going to decrease till 2. And it's going to increase from then on. So it's actually just these two guys here, which is actually... So I can do decreasing intervals, which is simply 0, 2. And that's going to be my answer for number 10. It's going to be relative max is 0, -3, as indicated here. Minimum is 2 and -7, indicated here. Increasing interval up to 0. And then, so from negative infinity to 0, it's going to be decreasing from 0 to 2, and then going to increasing from 2 to positive infinity. So this answer is correct in this case. So this is number 10. Let's do question 12. Let's do question 12 in this case. Oh, let's do 11 and then 12. I think we can do both of them. I think we can do both of them before the video ends. Let's do 11. So 11 here, we have a quadratic expression here. We have negative x squared plus 6x minus 4. And it's just simply a parabola, right? It's a parabola that's reflected along the x-axis, right? And transformed, I guess, it's actually shifted towards the right side in this case. And we talked about transformations in a previous course, so this is why I'm using this terminology to hopefully get you into the headspace of what we're thinking about right now. But is there let's do relative maximums and minimums. Is there a relative maximums and minimums? So let's write down relative max, relative min. So do we have a relative maximum? We do, right? We do have relative maximum in this case. This here is actually my absolute maximum, right? This, my function is not going to go, it's not going to go beyond this here is y equals, this point is y equals 5. It's not going to be greater than y equals 5. So in this case, I don't have a relative max, but I have a absolute max. I'm going to erase this and replace it with, this is the absolute max. And my absolute max in this case, again, this is a period of, this here is a period of increasing to decreasing, right? So I have maximum here. This is 3, 5 would be my absolute maximum in this case. 3, 5. And then do I have a relative minimum? Let's check. I don't actually have a relative minimum in this case. This is a period of increasing and the period of decreasing. There's no relative minimum in this case. So I'm going to say none. And if I don't have a relative minimum, I definitely don't have an absolute minimum as well. So this is none. Exclamation mark. And let's do intervals of increasing and decreasing now. So this here, I have increasing. And let's see, this is a period. Let's see, where are my periods of increasing? I'm going from here. This is from, I guess y is -8 all the way up to y equals 6. My period is now increased, right? So I can say from my x values are, this is negative infinity all the way up to 3, right? So, because that's when it switches to decreasing, right? So this is from negative infinity all the way up to 3. And then let's do decreasing. and we can use my maximum. Right? In this case, it would be 3, because that's where I started from, and it's going to head towards positive infinity. Positive infinity, right? And I can double check that with my graph. From 3 all the way to positive infinity as my x values is going to decrease, right? So I can verify that this indeed is correct. So from 3 to to positive infinity, my y values are indeed decreasing. Awesome. And let's do 12, and then we're going to wrap things up. Let's do question 12. Question 12, I have here y equals negative 25x, or sorry, yeah, negative 25x all over x squared plus 25. So we have a very, very unique rational expression in this case. So let's see, do we have a period of maximums or minimums? So let's check. So again, this period is decreasing because it's going. My values are going down, down, down. It's going to decrease. So it's going from a period of increasing and then going to a period of decreasing. So we have a relative maximum, or in this case, it's actually an absolute, but I'll write relative maximum and minimum first. So we do have a relative max and relative min. Relative max, relative min. So let's see if this x value is going to decrease all the way to, well, we don't know, right? It's going to decrease all the way. I think it's like a, this is a rational expression. So in this case, this here and this here, it's not going to, it'll never actually go, it's never going to go beyond whatever this y value point here is. I'm going to approximate around 3, right? And we can actually solve for this algebraically, and we'll get to that. But I'm assuming, I'm looking at this point here. It's kind of hard to see. I'm assuming this is negative 5. Yeah, I think it says negative 5. That's the kind of vertex of this curve here, and this is, I believe it's positive 5. It's kind of hard to see with the oh, I can't drag this. Can I drag this? Yeah, it's kind of hard to see here, but I'm going to assume here it's 5. So this is actually not my relative, but this is my absolute maximum, right? Because I told you in this case, it's never going to approach. It's not going to be greater than whatever this positive 3, and I'll solve for that, and that's not going to be lower than this negative 3 here. So in this case, I can change this to an absolute minimum, absolute maximum. So absolute max in this case would be this point here. This point here is, I'm going to say it's negative 5 and something. And I'll solve for that because I'm given my algebraic expression. And then minimum here would be 5 and some type of y value, right? So 5 and then some type of y value. I don't know that, but I know my x value is 5. So let's quickly solve for these y points here. So let's solve, let's do negative 5 first. So we have here, this is y equals, and we're just subbing a negative 5 into this function to solve for the x value. So it's negative 25 times negative 5 all over, this is negative 5 squared plus 25. Put that in my calculator. Let's see what I get. It's negative 25 times negative 5. And I have negative 5 squared plus 25. I'm going to get 2.5. So this here was 2.5. It's not technically 3, so I got that wrong actually, but I assumed it was 3. Can't really approximate. But so this here absolute maximum would be 2.5. And then let's do the, I'm going to sub y equals 5 in this case. So this is y equals negative 25 times 5 all over 5 squared plus 25. Let's sub in 5. Oh, sorry, I'm going to shift this over so you can see what I'm doing here. I'm going to sub in x equals 5 for my absolute minimum point. So I'll do that quickly on my calculator. So that's negative 25 times positive 5 all over 5 squared plus 25. I'm going to get negative 2.5. So this here is negative 2.5. So which means my absolute minimum is negative 2.5. So awesome. We solved for my, in this case, it was an absolute maximum and minimum. So let's do intervals of increasing and decreasing. move us up all the way here. So let's do, this is increasing intervals first. So periods of increase, or increasing. So let's do my periods of increasing. So as you can see here, it's going to increase here. My y values are increasing all the way up to a -5 in this case. So from negative infinity towards -5 would be a period of increase. Negative infinity to -5, and then it's going to decrease all the way here. And then at this point, this is a relative, or sorry, in this case, an absolute minimum. It's going to switch from a period of decrease to a period of increase, right? So from 5 towards positive infinity would be another period of increase. So I'm going to comma, this is 5 positive infinity. And let's do decreasing intervals now. So intervals of decrease is simply just this point here, right? So because remember I said that this is increasing, and then this would be decrease, and this is increase, right? So this is from -5 to 5 simply. So this is -5 to 5. And that's going to be our answer for question 12. So just a little review, and I'm just going to review all this because we actually covered quite a bit for today. I'm going to scroll back up, and I will zoom out of this, so you can see what we did so far today. We solved quite a bit today. So let's go back to this point here. And I'm just going to review what we did today. So today we talked about this concept of extrema. So this concept of points on the graph that are minimums and or maximums, and usually and maximums, minimums or maximums that exist on the function, right? So again, we specified a difference between relative and absolute minimum or maximum. So where again, for maximums, it's a period of increasing to a period of decreasing. My y values are increasing, and then it's going to reach a specific point where it's going to be my maximum, and then my y values start to decrease. That will be a point that will be a maximum, and then we define a minimum as a period of decreasing into a period of increasing. So that will be that's for relative minimums in this case. And then for absolute maximum, it's this function's highest and lowest point. So when we say that if some functions head towards positive and negative infinity, they won't have an absolute maximum or minimums. So sometimes relative maximums could be also defined as a absolute minimum or maximum as well. So those are the 2 points in terms of extrema that we talked about. And we talked about this concept of increasing and decreasing, right? So we talked about, I believe, in this, and we use interval notation in this case. I introduced you to that as well. But we have increasing intervals where I have, in this case, if we go back to example 1, my y values are increasing as my x values are also increasing. So from a period of, this is negative in x, at negative infinity all the way up to x equals -3, it's a period of increase, right? The y values are always consistently going up. If we extend the graph, this is going towards negative infinity, but if I'm going as x is increasing, it's going to increase as well with it. So I have a period or an interval from negative infinity to -3 that's increasing. And remember, my interval notations, I only care about my x values in this case. My y values, I know it's going to increase in y values, so I don't specify my y values. This is not a point in the graph. This is an interval notation. So it's simply denoting my x values. So we talked about increasing. And decreasing is just the opposite, right? So every time we have a point in which, so as the x values are approaching or between specific x values, my y values are always decreasing. So in this function here, in this graph here, from -3 all the way up to, I believe this here is x equals 1 here, this would be an interval of decrease, right? My y's are decreasing as between these two intervals. So today we talked about this concept of extrema, local and absolute maximum and minimums. We talked about intervals of increasing and decreasing, and I introduced you to this this notation of interval notation. So that's going to be all for today. For tomorrow, for the next lesson, what we're going to do is we're probably going to talk about this concept of kind of end behaviors and domain or ranges of specific functions. So stay tuned for that. It might be a little review from grade 11 or whatever your previous math course was. So stay tuned for that. And then we'll talk about other functions that might exist as well, and not specifically rational expressions or not specifically polynomial functions. So we're going to bring back kind of like piecewise functions or like square root functions and whatnot. So we'll use those functions to help us, and then we're gonna define the properties of those functions for next lesson. So as always, thank you so much for tuning in, and I will see you next time.